So thank you very much. What you're going to see in this presentation is a compilation of material, as was just said, in terms of it being partially what Angela developed that's specifically challenge related, and then part of my background, which was really in space crop production, which really served as the genesis for the Deep Space Food Challenge. And then I'll weave back and close with Angela's slides as well. And let's see if we can move this. All right, so Centennial challenges. So it's really a way that NASA can look beyond our organization to try to see how can people in commercial world help us in academia, help us solve some of these big issues which we have really are just coming to the forefront that we don't necessarily have the resources to engage in. And we're looking for new ideas. So it's leveraged off of the old Orteig Prize, which was, if you don't recall, was the first flight across the Atlantic, whether that was from New York to Paris, Paris to New York. Charles Lindbergh won that. Then there was the Ansari's X Prize, which was the competition, I believe, to send people up into the Kármán line, space at 100 kilometers, and do that flight 2 times in 2 weeks. And so it was the idea of incentivizing people to come up and solve issues or challenges that could leapfrog technology. And the thing about Centennial challenges, 1903 is when it started. It was first introduced, and it leverages off of the first flight with Orville and Wilbur Wright. And you can see by the illustration here, what life looked like at the time, what that plane was, but then what happened just a decade later. Planes were flying regularly during the First World War. After that, it just took off, and within 50 or 60 years, we were flying jets. So Centennial challenges specifically, as I mentioned, we're looking to expand the pool of potential solutions to meet specific research challenges, and we're doing that through this public prize competition. Again, we're looking for novel things outside of the mainstream that have promise. We don't expect that anyone is going to come up with an idea that we can just put a bow on, stick it in a spaceship, and solve a problem. But we are expecting people to come up with novel ideas that then, after further development and research, how they can be adapted to spaceflight eventually could make a big difference and improve the state of the art. And also there's the expectation that in a lot of cases, these technologies would have a commercial application that is appropriate for terrestrial use as well. So one of the big things about NASA is we're always trying to figure out how do we take what we do in space and leverage it to the advantage of people here on Earth. There are certain technologies that are probably a little bit out there, esoteric, that you might find hard to find that linkage, but when it comes to food, that's something that I have no problem selling NASA's investment in food because there's always a connection here. It was interesting for me personally coming to this meeting, not really heard of the organization before, but coming in and seeing people from the USDA, and we have collaborations with the USDA, seeing a talk from someone from McGill, having been to McGill as part of my space science work. So there's a lot of connections that, again, we talked a little bit at the lunch break about being siloed. We're all siloed in some way, but when you see and you can look over the edge of that silo, you'll see people doing a lot of things that relate tangentially to what you're doing. And so I think that's important. I think it's time to break those silos down. And I think in a way, Centennial Challenges helps us to do that. So let's see. Motivations for a Centennial Challenge. Well, it's more than just a prize purse. There are hard incentives and there are soft incentives. A lot of times we'll see companies that are startups, have people who are very engaged in making a difference in the future. They want to go out and they want to solve problems that are interesting and challenging to them that no one has done before. And a lot of times that's a benefit, more so than the prize money that's associated with the challenge, to get people interested and excited in working with the challenge. And as a former NASA employee, I know that anytime people can work with NASA, there seems to be this leap jump to do that because of the brand name that we've managed to set up over time. So let's talk a little bit about technology driving exploration. As you can see in this chart, this is all space related, but you can see there are a lot of different areas where it's going to take leaps in technology to be able to pull off actually putting a permanent outpost or base on the moon and a permanent outpost on Mars. And there are things that you can see. It's not just the transportation systems. It's not just the sustainable aspects of working and living on the land, but it's also the discoveries we're going to make along the way, and how can I take this knowledge and incentivize the commercial markets to see that there's benefit there to doing that to continue on. So our motto is go land, live, and explore, and that's what we're trying to do. Current Centennial challenges, there are 3 going on right now. Again, you can see they're all focused on making life on the moon or life on Mars something that's really achievable. So the first one is what's on the moon. Again, that's looking at how do I create power systems there to feed the infrastructure we're going to have on the moon. I've been told that when we get to the moon, we talk about, again, my background in crop production, we're looking at habitable modules that we're going to fill with plants, and one of the first questions is, well, how am I going to, how much power is it going to take? Well, we have to give them the answers on power, but I've been told, don't worry about that too much because there'll be plenty of power. Power will not be the limitation when we go. So there are ways we're looking at addressing that. The challenge What's on the Moon is going to look to do that as well. And then why are we going to the moon? Well, we can go to the moon, especially the South Polar region, because we know that there's water there. But how do I access that water? We thought at first that the water would be in the dark side of craters that have never seen sunlight. That may be true, but recent science studies and investigations have shown that it might be as much as 10 meters down below the surface. So how do we excavate that material, access the water, pull it out, because we're not going to be able to do the things we want to do on the moon for the reasons we want to go there if we can't access that water. And then there's the deep space food challenge. I tell people that first thing you do when you want to go on a trip and a vacation is you plan everything, you think of all the places you're going to go, you're focused totally on that, you make your reservations. You get on your plane, you fly there, and you land, and what's the first thing you do when you get there? You want to find a place to eat. You never really thought about that before you go, but as soon as you get there, that's an important thing. So we can't wait until we arrive to figure out how are we going to eat. We'll talk a little bit more in a few slides as to how we do that now and how we're looking to change that. So now we have a little embedded video because I thought it might be more interesting to hear from Alton Brown than from me. So he's going to introduce the challenge. All right, so we'll dive a little bit into more of some of the things that Alton mentions in that video. Again, just the summary statement for the challenge itself, we're looking to create novel food production technologies. And again, important here is that they require minimal inputs and that they maximize the safety both of the output as well as the hardware in the operation. And that food output is nutritious and palatable. We know from history that if astronauts don't like what they're given to eat, they will eventually, over time, as menu fatigue sets in, stop eating and lose weight. So that's an important aspect of it. And right now the focus is on long duration missions. So again, I'll talk a little bit in a couple of slides about how we feed astronauts now and why this becomes a real issue for us when I start talking about going beyond low Earth orbit. And again, the input is that we want to be able to have the potential to benefit people on Earth. Just a summary, challenge leaders and partners. Again, the key thing here is, again, reiterating the fact that the Canadian Space Station is involved. Centennial Challenges does work with allied organizations, so they help do a lot of the external coordination and provide the support that the agency itself doesn't have the ability to do. And again, the lead center for the food challenge is the Kennedy Space Center, which is where I come from. So big for us in this challenge is that this is actually the first of its kind a collaboration between NASA and the Canadian Space Agency. So they're actually offering a parallel prize competition, slightly different motivations. They're focused as much, if not more, on how do they take some systems and ideas that they come up with and apply them to feeding the populations out in the northern territories of Canada that doesn't have ready access to the fresh foods and vegetables that we necessarily need. So how can they maximize that? Matt will talk about that in a little bit. And again, one of the great aspects of this whole collaboration is that I've known Matt for a number of years. I've known the other people who'll be speaking today. So you've got this very small cadre of people who are working in this space. I think when we think about USDA feeding people on Earth, there's big organizations pooling together lots of brain power and talent. When it comes to feeding people on the surface of the moon or Mars, it's a very small group of people. So we really depend heavily on what's being done terrestrially to be able to make that progress and leap forward into deep space. So let's talk a little bit about, now we're transitioning into my slides. Where does this all come from? How do I relate this to the past? A lot of times I will hear people thinking about food and exploration as it's some kind of new idea, like we've never had to do this before. But the people who work in this field, they always seem to go back at the history, and I think this is very appropriate, and look at the history of food and exploration. And when you go back to the most recent cases, you're looking at polar exploration. So go back about 170 years ago. Think about what was going on with trying to find a Northwest Passage, trying to get to the South Pole, get to the North Pole, and what were the food systems that the people used and engaged and brought with them. So if you look at that, it's interesting to see that the Franklin expedition had a large crew. It was financed heavily by England. It was probably them trying to find the Northwest Passage was like us going to Mars today. It was this big technical challenge, operational challenge. And they wound up doing the best they could, but they failed. Same thing with Robert Scott. He managed to get to the South Pole, but on his way back from the South Pole to his space station, he and 5 of his crew members wound up perishing. It took Roald Amundsen, with just a crew of 7 in a very small boat, but using the right principles and idea, understanding the mission completely, understanding what it took to be successful, leveraging the experience of others to be successful. And it's that kind of knowledge we're trying to take with us. It's not enough to just throw money at a problem. We have to be able to really learn from the past, understand the hazards, try to focus on the logistics. How do we do that? And so our food system work eventually has to take all this into account. And we have to be creative and innovative and not just depend on how things were done in the past. Go back 100 years even before that, and we start looking at folks like James Lind. He was a Scottish doctor. He was basically a pioneer in naval hygiene and research for the Royal Navy. It was he who came up with the idea and the thought process that there was something with scurvy, which was the big killer and disruptor. Battles were won and lost over scurvy on naval crews, where fresh citrus fruits came to play and how that would mitigate the effects of scurvy. He didn't know about vitamin C. Vitamins weren't discovered until, I guess, the beginning of the 20th century. But he was smart enough and aware enough that if you fed crews properly and you gave them the right meals, that they would be resilient. And so I put this quote in here from him in his book, The Health of Seamen in the Royal Navy. To a crew replete in health, what enterprise too dangerous, what achievement too great. And I think that's the mantra we're trying to work in today. We can feed our crews on missions of exploration that are risky, hazardous, long, lots of deprivations along the way, far from home, minimal chance for rescue, resupply. If we keep them fed, we keep them operating at peak efficiency, really emphasize their behavioral health and performance, that's going to give them the best chance to be successful. So the technology and landscape, how do I take all this and apply it to where we are today? So this is kind of like the layout where we are with space food systems. So right now we depend on the International Space Station on resupply. So we have relatively good access to low Earth orbit, and fresh food is set up there periodically, but all the main dietary components are part of the prepackaged menu, which has really changed over time. In the early days, I think from the US side, John Glenn was the first person to actually demonstrate that he could eat and drink something in space. And it was a tube of applesauce and some sugar tablets. And actually, the tube of applesauce is in the Smithsonian right now, too, supposedly. So they keep that. And so we really depend on the prepackaged food. When I start going to the moon and Mars, moon first is going to be a question of, how do I afford and maintain the logistical resupply of this food. Again, the food itself, the prepackaged food that we have, after about 18 months, it starts to degrade in certain key vitamins and nutrients. So we already know that the big problem, the first thing we have to solve for a long duration trip to Mars is how do I keep the food viable for that mission? But for the surface of the moon, we're going to be focusing on not only developing these food system concepts, but we're going to be looking at how do I minimize resupply that we would need to provide on the moon. And so, again, the importance of a viable food system is something we can't overlook. That's kind of the landscape. So let's talk about key aspects of a viable food system. I think when you look at this chart, you will see these topics and how closely they relate to the things that you folks are doing for terrestrial food systems. And I'll go through each of them. So first of all, the food must be safe. This is the most important thing, and I think the thing that when you get new players into this field, I don't know that they completely appreciate the importance of food safety. It's easy, relatively, to come up with an idea and approach for how you can do something new and novel. But if you've never been in the food space before, making that such that it's food safe and it passes all the check marks is a big challenge. It's something that requires a light bulb to go off in people's heads sometime. And doing that on a space mission is probably even more important because you've got a crew of probably 4 to 6 people. They're heading out. They don't have access to maybe the kind of medical technology that would be able to mitigate a severe sickness. And so it's extremely important in everything we do. As is the nutrition. It has to be able to, again, for the relatively near-term, long-distance flights, we're looking at nutritional supplementation more so than calorie replacement. And so that has to be nutritious. The food systems have to be usable. So the way that the astronauts grow the food has to be something that's usable, has to minimize crew time. When we get to the moon, we're not sending astronauts there to be farmers. We're sending them there to do exploration. And so I've seen concepts where people have come up with these very elaborate schemes to produce crops on the surface of the moon that require practically 1 or 2 crew members spending their full waking hours tending it. And that's just not a viable approach. So it has to be a usable system. And when the humans engage it, the real hope would be that there would be a psychosocial benefit of engaging with it. So that's where early on with plants, that's an easy sell because people like to grow and tend plants. They get a behavioral health and performance benefit just from doing that. Other systems may be less so, but even so, it has to be something that's relatively easy for crew members to engage in. Then resource minimization. Again, everything is dependent on how efficient I can make these systems. Do I get as much output out as what I put into it? If I'm putting more into a system than I'm getting out as edible food product, that's not going to fly, literally. Reliability. When I'm at the moon or I'm at Mars especially, the reliability of these systems is such that it has to be something that we try to focus on. Survivability on a 3 to 5 year mission is a minimum. Everything we take with us on a trip to Mars is all we have. So from a spare parts perspective, one of the things we look at is how do I commonly use components across systems. So anything we come up with in the food arena where we can adapt common components is going to be a benefit. And then variety. As I mentioned, menu fatigue is a real challenge. On the International Space Station right now, I think we have something on the order of 250 ingredients or meal packages that go into the diet that's repeated periodically. We're not going to have that flexibility on a mission to Mars, again, because we're going to have to take everything with us. And so how do we increase variety? And so our thought is that crop production, even things, and not to be a negative, but even things as simple as microgreens, potentially have a huge influence on how you can change variety and palatability of these foods and doing it very efficiently with minimal resources. And that goes along with palatability. And then there's the stability. And that's the real elephant in the room, and that everything we've done to date with crop production, anything related to food, has been done in low Earth orbit under the protection of the Earth's magnetic field and the Van Allen radiation belts. So we don't have the exposure that we're going to see once we go beyond low Earth orbit. And again, we've only had limited time beyond low Earth orbit with the Apollo astronauts. And so we fully expect that the radiation will be a factor, not only for the humans, but for the food production approaches that we take, especially the plants as well. Theory says that if the humans can tolerate things, the plants will be able to tolerate it, but we've never done any testing to even validate that assumption. All right, so again, here is where I really delve into the work that I've been doing over the past 5 or 6 years. And it was, how do I take what we're doing today on the ground in low Earth orbit, and how do I extrapolate that into a realistic and credible roadmap for deep space exploration? So in the lower left-hand corner, you can see the work we do on the ground today basically is doing fundamental research, not only in the systems to grow plants, also in the plant cultivars themselves, what types, species, what are the stresses that are applied to the plants in low Earth orbit. Understanding those stresses, microgravity plays a big role in how you manage air and water to the root zone, and how do you mitigate those stresses based on the different systems, techniques, and the plant cultivars that are selected. Genetic engineering gets in here a little bit. If I'm trying to maximize the food output in a given volume, if I'm looking at, for example, growing things like tomatoes, I want to get the most fruit out of that tomato. The inedible portions are less important to me, so whatever I can do to maximize that is a potential, but GMO in space has as much complication as it does here on Earth currently, so we have to do that judiciously. What we're looking at first off is using known cultivars of plants that are familiar, then working with breeders to kind of breed the desired traits we want, and the last resort would be GMO crops at this time. So we do that right now when we work and we fly things to the International Space Station. In a couple of slides, I'll show you what those systems that we currently have are today. But after that, we're looking at now branching out beyond low Earth orbit. We're going to have the gateway up in cislunar space, which will be the jump-off point for astronauts to get to the surface of the moon. There's the hope we'll be able to have space at gateway to at least conduct fundamental research on plant behavior in this deep space environment. And then eventually we're going to get to the moon. At first, I would expect that the food system for early returning astronauts to the moon is going to be highly constricted. So you're going to see a vibrant system that was a food system on the International Space Station really constrained when I go to the surface of the moon initially. Talks are that astronauts are going to be highly limited in the amount of water they're going to be able to take with them, and maybe given only 30 minutes a day or twice a day to prepare their meals and consume them. So we're not expecting much at the beginning. It's going to be harder. But then once we start developing that surface infrastructure, I expand to a habitat on the surface of the moon. I expand with all the rover capability, the power stations, et cetera. Now we're going to be looking at expanding the capability for the food system. As crew sizes increase, maybe getting into the tens, we're going to be looking at semi-permanent to permanent outposts there. Food is going to become critically important. None of the focus in the agency right now is on that surface food production capability. We're too focused because of the limitations in funds. I don't want to say too focused, but we're very focused because of limitations in funds on just building up the infrastructure and dealing with all the technical hardware challenges for actually getting to the surface of the moon and working on the surface of the moon. But eventually we're going to use the moon as a way to leverage the work we do there and bring it with us to Mars. So that's the end game. But you'll see that where it says up on the upper right corner, this early Mars missions and Mars transit. So it's that Mars transit, which interestingly enough is going to happen probably after I get the early surface outposts on the moon. That's the one where we know we're going to need to take some food production capability with us, simply because it's a 3-year mission depending on the propellant source and the propulsion source. And in that 3-year mission, we know we're going to see a degradation of key vitamins and nutrients, so we have to account for that. And so right now, we're actually focusing work on the International Space Station, planning for that transit mission to Mars. So let's talk a little about the challenges. While most of these relate to space flight, you'll see ones in here that relate to terrestrial agriculture. So we've got deep space, we have to worry about microgravity, fluid movement, and the fact that there's no convection. So we constantly have to figure out, how do I get that? How do I keep the plant leaves cool? How do I let them to transpire appropriately? Again, we have to collect the water from transpiration, which is pure water, put it back into the system so I'm not constantly having to feed the system with water. Surface, we have dust, regolith, and partial gravity. The only thing I want to say about that is when I came into this aspect of my NASA career, the movie The Martian was obviously, part of that. Actually, Buzz Aldrin told me I had to go see it, and so I did. But the key thing about regolith is that every other system that's working on the surface of the moon is trying to figure out, how do I keep it out of the habitable environment? So the very idea of bringing it in, let alone remediating it from the things that would be counterproductive to plant growth, to augmenting it with nutrients and capabilities so the plants could grow and thrive, becomes problematic, as is the fact that regolith, from the movie you'll remember this, is really more of an area solution. It's thinking about how do we take terrestrial agriculture and apply it to the surface of another world. When we get there, we're not going to be terraforming. We're going to be working in closed environments, much more like urban farms or vertical farms. And so how do I maximize the volume is the key. It's not an area solution. So we have to figure out what's the real role for regolith in the future. Then we talk about the crops. So we have a lot of different aspects of the crops, and here's where you're going to see things that are somewhat unique to space. High CO2. The environment on the International Space Station can have 2,000 ppm of CO2 regularly, so that's not something that plants are used to growing in here on Earth, and we have to understand how certain plants thrive in higher CO2 environments, certain do much poorer. So we have to understand that. Food safety and microbiome, that affects everybody in this room or whether it's talking about space. Same with nutrient output. The sustainability of the process, again, is important. Vehicle resources and crew time. So in a way that equates to the terrestrial commercial market, where how am I looking at what's my costs, what are my operational expenses for maintaining a system like a controlled environment agriculture system. Fortunately at NASA, when it comes to the CapEx side of that equation, we don't really worry about that. When it comes to building a food system, take with us on a long duration mission or take with us as an early surface mission, the costs of that are going to be minuscule compared to the overall mission costs. Then we have productivity, stress tolerance, again important here as well, environmental optimization, crop scheduling. So you see that there's some challenges that are unique, some that are common. Now, operational challenges, these are challenges that people in this room might not have spent that much time thinking about. When I go to a Mars mission, for example, depending on the planetary alignment, round-trip communications could be up to 45 minutes in duration. So I can't always depend on an astronaut being able to reach out and get an immediate response from somebody on the ground back here at Houston to tell him what to do if there's an issue. So we have to take that into account when it comes to the design of the systems and how do we handle problems. Again, focus changes from replacement to repair. Because we have such good access to low Earth orbit, if a system fails, the historical way we deal with that is we fly up a spare on the next operational flight that we can do that with. Well, if I'm on Mars, that's a 2-year mission, round trip to get there, or one way, sorry, to get there. And so to do that becomes problematic. And so I really want to focus on how can I maintain that system? How do I repair it? How do I make it such that crew members there can work and fix something that breaks without having to rely on a whole replacement unit being sent? We also need systems and software controls that detect problems, decide what to do about it, and go make those fixes. So we want to take the human out of the loop as much as possible by having smart sensors, smart control systems that can see things before they ever go south where the human eye could detect them. And then the vehicle systems need to be evolvable. Talked a little bit about the fact that we can't replace things. Well, we can't constantly be sending up new versions of something. We have to be able to take the system core that's there, enhance it and increase its capability and performance by evolving that system rather than throwing it out and replacing it with something totally different. And then another aspect, especially from the plant world, that becomes challenging is the fact of vehicle dormancy. So there'll be periods of time where, long periods of time, probably up to a year, where I'll have astronauts at some location, they're going to depart, and it may be months before another crew comes. How do I keep systems like that up and operational? Things where I have water and biofilms, potential for biofouling in there. What am I going to do about that? How am I going to maintain those systems? A little bit about where we are today. So we have 2 basic plant research facilities on the International Space Station. Most all the film and video you will have seen of images of astronauts growing plants is generally from 1 or 2 of these systems. It's either the veggie payload, of which we have 2, or the advanced plant habitat. Key about these is that these are both research systems. They are not production systems. We've kind of leveraged to use them that way recently by letting astronauts eat what they've grown, but they were never designed for production. By the very definition, you can see the output there. It's not significant enough to feed anybody, not even a salad a day. The difference between the two is veggie is open to the cabin environment. So for veggie, we have to have astronauts watering it regularly because that transpired water just goes back into the crew compartment. Advanced plant habitat, the opposite extreme. It's much more capable system. It's closed, it's highly instrumented. So you've got basically the Ford Pinto and the Lincoln Continental versions of things. But again, they're research payloads. So what's the next step? Well, I was fortunate before the end of my career to get funding for this payload that we're calling Ohalo 3. It will be the first operational crop production system designed for continuous food production. So the reason we got funding for this is going to serve as a prototype for that system we eventually put on the Mars transit vehicle. A little bit about the name. I was trying to think of what would you name this thing. And I was doing some research and I found that there was this place located on the Sea of Galilee in Israel, Ohalo 2. And basically, archaeologists have looked there, and Ohalo means my tent. They basically found the remnants of an old settlement, 23,000 years old. They found over 150,000 specimens of plant remains, and it's the first earliest known small-scale evidence for plant cultivation, approximately 11,000 years before the onset of agriculture as we know it today. So we said, what more appropriate thing to do than name the first system that we take beyond Earth after it in honor of that, so we're calling it Ohalo 3. All right, so segueing back into the reason for a challenge. So the challenge has merits for space. You know, ultimately, at the end of the day, the goal at the end of the rainbow is that we need to have a permanent bioregenerative life support system on the surface of the Moon and Mars. We're going to need that to kind of cut the umbilical back to Earth as best we can. And the benefits of that are low food stowage mass. Again, we get to treat the water and waste, so you're all interested in doing that kind of thing here as well. Air revitalization, the improvement in nutrition and acceptability. Personalized nutrition will be important then as well. And then another big thing that actually, you know, when budgets start to constrain where we are now, the actual behavioral health and performance benefits of fresh food sometimes can be seen to outweigh the prepackaged food that we have, thinking that, well, we don't really need the fresh stuff. But the astronauts' response to having something fresh, something reminiscent of home, when I basically stripped them away from their known environment, put them in this isolated, sterile environment, is something that's very important and can't be overlooked. And now why a challenge for Earth, the technology for Earth aspect of it? Again, it relates to food insecurity. I say at presentations now and then that people here are worried about feeding a population of 10 billion people by the year 2050. I'm worried about feeding a crew of 4 to 6, maybe in that same time frame. So you guys have the hard work. You guys are doing the important work. That's why we are going to be leveraging on a lot of what you guys do. But again, what can we help with? Well, the cost to provide fresh food. How do I get food systems into remote areas? How do I increase the shelf life and the quality of the food that we deliver here terrestrially? Again, we see systems that you would deploy on the Moon and Mars as having relevance to the type of systems you might take and deploy in areas where there's been disasters, where the supply chain has been interrupted, that you can produce food on the spot. And improved food technologies can benefit both, excuse me, can be a cost-effective way to address food production in remote environments. It allows us to deploy successfully, commercially viably, food production near urban centers, and again, response in case of humanitarian disasters. So that's kind of the story of food production from the Deep Space Food Challenge into why we came up with that idea in terms of what we're doing for crop production, and then all back to the closure for what that means for the Earth. So the challenge, again, just to finish up here real quick, we've had 2 rounds of the challenge so far. We started with 18 US teams and 10 named winners and 10 international teams. When we got to phase 2 of the challenge, we whittled that down to 5 US teams to be phase 2 winners and 3 international teams. Where are we now? Well, fortunately, you're going to hear later this afternoon from 2 of those teams. Interstellar Lab will be here. Barbara Belvisi will talk about their work, and we have from the US side, and we have Solar Foods here, and Arttu Luukkonen will be here talking about what they do. I think you'll find both those presentations very interesting because, again, there's relevance both terrestrially and for space. And NASA's goals for phase 3, what we did in the phase 2 is we basically went through one production cycle of their system. Now we're going to look for the repeatability, the reliability in the process. Everybody has learned. They've got more insights as to the challenges we're doing. We're going to work them through it. We also decided that instead of having just the companies and the challenge teams operate their hardware, we were going to farm out for simulated astronauts, simunauts, to be trained and then work on their hardware to show what it would be like for an astronaut. Is the system really usable? So we'll be doing that in round 3 of this scenario, of the challenge. And the simunauts that we're getting, we're fortunate because our allied organization, the Methuselah Foundation, has managed to engage folks at Ohio State University. So we're going to be using Ohio State University students. We're going to be leveraging on a lot of the capability they have there in food system technology. We're going to be doing food safety assessments on everything that's produced. We're going to be doing sensory testing as well. And we're going to be doing a nutritional analysis. So sensory testing is one thing we hadn't done before. And we're actually interested to see what the outcomes are. It's one thing to create a food product. It's another thing to make it palatable. How much do we have to add or manipulate that output, regardless of how healthful and beneficial is it, to make it something the astronauts will eat? So we'll be looking at that as well. Right now, we're looking at completing the contest at the end of August, where we'll announce the phase 3 winners. And we'll be looking at one top-scoring U.S. team awarded $750,000, 2 runner-ups, $250,000. And one top-scoring international team will be recognized as the winner with 2 runners-up for them. And I think that's about it. So if you have any time for questions, I don't know. Okay, no time. I spoke too long.